Welcome to AudioDocs by Platform-Engineering-Playbook, where we transform open-source documentation into audio you can learn from anywhere. Each episode aspires to adapt official project docs into digestible audio, explaining concepts clearly using conversational explanations that are easier to absorb on the go. Everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. If you find this useful, please like and subscribe. And if you catch any mistakes, please leave a comment or open a pull request to help make the playbook smarter. The episode transcripts are open source at platform-engineering-playbook.com. Let's get into it.
This is AudioDocs, covering CoreDNS version 1.13.1. I'm going to walk you through the complete official documentation for CoreDNS, the default DNS server for Kubernetes. Every time a pod looks up a service by name, every time your application resolves cluster.local, every time kubectl exec needs to find a pod, CoreDNS handles that resolution. In this episode, we'll cover the plugin architecture that makes CoreDNS so flexible, how to configure the Corefile and server blocks, installation options for Kubernetes and standalone deployments, deep dives into the most important plugins, Kubernetes, forward, cache, file, hosts, and more, monitoring with Prometheus metrics, and security features, including DNSSEC and access control. This documentation is based on CoreDNS version 1.13.1, released October 2025. Let's start with the history and context of the project.
Let's talk about where CoreDNS came from and why it matters. CoreDNS was created by Meek Gibbon in March 2016. Meek is a DNS expert who wrote GoDNS, the most popular DNS library in Go. He was pondering whether he could create something like Caddy, the popular web server, but for DNS. The initial prototype was called KaddyDNS, a fork of the Caddy web server that answered DNS queries instead of HTTP requests. Within a week, he had it answering real DNS queries. The experiment worked so well that it became a dedicated project renamed to CoreDNS. Here's the key insight that made CoreDNS different. Traditional DNS servers like Bind are monolithic. They have all their functionality built in, configured through complex zone files. CoreDNS took a radically different approach. Everything is a plugin. Want caching? Add the cache plugin. Want to forward queries upstream? Add the forward plugin. Want to serve Kubernetes services? Add the Kubernetes plugin. This plugin model means CoreDNS can be exactly what you need and nothing more. In March 2017, CoreDNS joined the CNCF as a sandbox project. The goal was clear: become the cloud-native DNS server. That bet paid off. In December 2018, CoreDNS became a CNCF graduated project, the same status as Kubernetes itself. More importantly, in Kubernetes 1.11, released in June 2018, CoreDNS became the default cluster DNS, replacing kube-dns. Today, every Kubernetes cluster runs CoreDNS. It has over 12,000 GitHub stars and more than 400 contributors. The project releases regularly, with the current version being 1.13.1. If you're running Kubernetes, you're running CoreDNS. Understanding it isn't optional. Let's talk about how CoreDNS fits into your platform architecture. Think of it as the phone book for your cluster. In a typical Kubernetes setup, CoreDNS runs as a deployment in the kube system namespace, usually 2 replicas for high availability. Every pod in your cluster has its DNS resolution pointed at CoreDNS by default. Here's the data flow. A pod wants to reach myservice.default.svc.cluster.local. The pod's kubelet configures its resolve.conf to point to CoreDNS. The DNS query goes to CoreDNS. CoreDNS looks up the service in its Kubernetes plugin cache. CoreDNS returns the cluster IP. The pod connects. This happens hundreds or thousands of times per second in a busy cluster. Every service-to-service call starts with DNS. What does CoreDNS depend on? Essentially nothing. It's a statically compiled Go binary. No external runtime, no library dependencies. The Docker image is literally Scratch, CoreDNS, and TLS certificates. That's it. What depends on CoreDNS? Everything. Your applications, your jobs, your controllers, kubectl exec. If CoreDNS is down, your cluster is effectively broken. Let me give you the mental model. CoreDNS is like a Lego set for DNS. Each plugin is a brick. You stack them together in your Corefile configuration. The order matters, but that order is defined at compile time, not configuration time. Where is CoreDNS good? Kubernetes service discovery, internal DNS for microservices, recursive resolver for outbound queries, custom DNS logic with the template plugin, split horizon DNS with views. Where is CoreDNS not the best choice? If you need authoritative DNS for millions of records, you probably want dedicated DNS infrastructure like Route 53 or Cloud DNS. CoreDNS can do it, but that's not its sweet spot. Here's how CoreDNS connects to other things in your cluster. It reads from the Kubernetes API to know about services and endpoints. It can forward to external DNS servers for domains outside cluster.local. It exposes Prometheus metrics for your monitoring. It integrates with Cert Manager for DNS 01 challenges if you're doing Acme. The beauty of CoreDNS is its simplicity. It's one thing doing one job extremely well.
Before we dive into the documentation, let's cover the key concepts you need to understand CoreDNS. First, the core file. This is CoreDNS's configuration file. When CoreDNS starts, it looks for a file named Corefile in the current directory, unless you specify a different path with the -conf flag. Everything about CoreDNS behavior is defined here. The core file is organized into server blocks. Each server block defines a DNS server for one or more zones. A zone is a DNS domain that this server is authoritative for. The simplest server block looks like this: a dot representing the root zone, followed by curly braces containing your plugins. The dot zone means handle everything. If you specify a more specific zone, like example.com, CoreDNS will only handle queries for that domain and its subdomains. Inside each server block, you list plugins. Plugins are the building blocks of CoreDNS. Each plugin does one thing. The cache plugin caches responses. The forward plugin forwards queries upstream. The Kubernetes plugin resolves Kubernetes service names. Here's a critical concept. The order you list plugins in your core file does not determine their execution order. The execution order is baked into CoreDNS at compile time, defined in a file called plugin.cfg. This catches a lot of people off guard. Why this design? It prevents configuration errors. You can't accidentally put caching after the response is sent. The plugin chain is deterministic. Plugins can have directives, additional configuration within the plugin. Some plugins are simple, taking just a name. Others are complex, with full configuration blocks of their own. One more thing: environment variables. CoreDNS supports environment variable substitution in your core file. Use the syntax $, curly brace, variable name, close brace. CoreDNS substitutes these values when parsing the configuration. With these concepts, core file, server blocks, zones, plugins, and directives, you're ready to understand everything else about CoreDNS configuration. Let's talk about getting CoreDNS installed and running. CoreDNS is written in Go, which means you get a single static binary with no external dependencies. No runtime to install, no library paths to configure, just the binary.
The easiest way to get CoreDNS is to download a pre-compiled binary from the GitHub releases page. Every release includes binaries for Linux, macOS, Windows, and various CPU architectures, including ARM and PowerPC. Download it, make it executable, and you're ready to go. If you prefer containers, CoreDNS publishes official Docker images to Docker Hub under CoreDNS/CoreDNS. The image is minimal. It's Scratch base plus the CoreDNS binary plus TLS certificates for DNS over TLS, DNS over HTTPS, and gRPC. Nothing else. For Kubernetes specifically, you'll usually deploy CoreDNS through Helm or kubectl apply with the official manifests. The CoreDNS deployment repository on GitHub has everything you need. In most cases, if you're using a managed Kubernetes service or a standard installer like kube-dns, CoreDNS comes pre-installed. If you want to build from source, you'll need a working Go environment. The CoreDNS repository README has current instructions. Generally, it's clone the repo, run make, and you get a CoreDNS binary. Building from source is actually common for one specific reason: adding external plugins. The default CoreDNS binary includes about 30 plugins. If you need one of the 40+ external plugins, you need to compile CoreDNS with that plugin included. To test that CoreDNS is working, you can run it without any configuration. By default, it loads the Huami plugin, which responds to any query with the client's IP address and port. Start CoreDNS with -dns.port = 1053 to use a non-privileged port for testing. Then use dig to send a query. In Kubernetes, you can verify CoreDNS is working by execing into any pod and running nslookup or dig against the kubernetes.default.svc.cluster.local service. If that resolves, CoreDNS is handling your cluster DNS correctly. For production Kubernetes deployments, you'll want at least 2 replicas for high availability, resource limits set appropriately, and proper node affinity to spread pods across nodes. The default deployment handles most of this, but verify your settings match your cluster's needs. Let's dive deep into the Corefile, CoreDNS's configuration file. The Corefile consists of one or more server blocks. Each server block starts with the zones the server should handle, followed by curly braces containing plugin configurations. The simplest possible Corefile is just a dot, open brace, close brace. The dot represents the root zone. This server handles everything. You can specify specific zones like example.com or CoreDNS.io. Multiple zones on the same line share the same plugin configuration. By default, CoreDNS listens on port 53. To change this, add a colon and the port number after your zone. For example, .:1053 makes CoreDNS listen on port 1053. Here's an important note. If you explicitly set a port in the Corefile, you cannot override it with the -dns.port command line flag. You cannot have 2 server blocks for the same zone on the same port. CoreDNS will error on startup if you try. However, you can have the same zone on different ports. And with the bind plugin, you can have the same zone on the same port as long as they bind to different network interfaces. CoreDNS supports multiple protocols. The default is plain DNS over UDP and TCP. But you can also configure DNS over TLS, DNS over HTTPS, and DNS over gRP. You specify the protocol by prefixing your zone with a scheme. DNS dot for plain DNS, TLS dot for DNS over TLS, HTTPS dot for DNS over HTTPS, and gRP dot for DNS over gRP. Inside a server block, you list your plugins. The simplest form is just the plugin name on its own line. For example, adding Chaos to your server block enables the Chaos plugin, which responds to queries about CoreDNS version. Most plugins accept additional configuration through directives. These go on the same line as the plugin or in a block underneath it. The Chaos plugin, for example, accepts version and author directives. More complex plugins have their own configuration blocks with curly braces. Here's a practical example. Say you want CoreDNS to serve 4 zones on 2 different ports. You might have CoreDNS.io on port 5300 serving zone files, example.io and example.net on port 53 also serving zone files, and the root zone on port 53 handling Kubernetes service discovery plus forwarding to Upstream DNS. Each of these is a separate server block in your Corefile. Environment variables work anywhere in the Corefile. Use $, open brace, variable name, close brace. CoreDNS substitutes the value when parsing. This is useful for keeping secrets out of your configuration files. The import directive lets you split your configuration across multiple files. You can import a file from anywhere or use snippets. Snippets are named blocks defined with parentheses that you can include multiple times. Define a snippet once with standard plugins like Prometheus, Log, and Errors, then import it into every server block. Common errors to watch for: putting a plugin name outside a server block makes CoreDNS think it's a zone name. If you see unknown directive errors about a period or another plugin name, check your brace matching. Also remember that plugin order in the Corefile doesn't determine execution order. That's fixed at compile time. The configuration is actually quite simple once you internalize the structure: zones, server blocks, plugins, and directives. Everything else is just applying this pattern. Let's walk through some common CoreDNS setups you'll encounter in production. The first setup is authoritative serving from zone files. This is classic DNS server behavior. You have a zone file, CoreDNS serves it. The file plugin handles this. Say you want to serve the example.org domain. Create a zone file, traditionally named something like db.example.org. Inside, you define your SOA record, your NS records, and your actual DNS records. A records for IPv4, AAA records for IPv6, and whatever else you need. Your Corefile just specifies the zone and points the file plugin at your zone file. Add the log plugin if you want to see queries. Start CoreDNS, query it with dig, and you'll see your records. The log output tells you exactly what's happening: the client address, the query type and name, the protocol used, the request size, the response code, response flags, response size, and how long it took. This is your debugging goldmine. The second setup is forwarding. This is probably the most common use case. CoreDNS receives queries and forwards them to Upstream resolvers. The forward plugin makes this simple. In your Corefile, specify the root zone and tell forward to send everything to your Upstream servers. You can list multiple Upstreams for redundancy: Google's 8.8.8.8, Quad9's 9.9.9, or your corporate DNS servers. CoreDNS will load balance between them and handle failures automatically. The third setup is split forwarding: different domains going to different Upstreams. This is extremely common in enterprise environments. Internal domains go to your internal DNS. Everything else goes to public resolvers. There are 2 ways to configure this. You can use multiple forward statements in one server block, each matching different domains, or you can use multiple server blocks, one per domain. The second approach is cleaner and lets CoreDNS handle edge cases like DS queries correctly. For example, your internal corp.example.com goes to your internal DNS at 10.0.0.53. Everything else goes to whatever's in etc resolveconf. 2 server blocks, clean separation. The fourth setup is recursive resolution. CoreDNS doesn't have a native recursive resolver in Go, but the external Unbound plugin wraps libunbound. This lets CoreDNS act as a full recursive resolver, walking the DNS hierarchy from root servers down.
To use Unbound, you need to recompile CoreDNS with the plugin included. It requires cgo and links against libunbound, so your binary is no longer fully static. In your Corefile, you enable Unbound, add the cache plugin for performance, and you have a recursive resolver. One key point about the cache plugin with Unbound: it disables Unbound's internal cache so CoreDNS's cache metrics work properly. You get unified observability. These setups cover most production scenarios: serving authoritative zones, forwarding to upstreams, split DNS, and recursive resolution. You can combine them: authoritative for some zones, forwarding for others, all in the same Corefile.
The Kubernetes plugin is probably why you're running CoreDNS. It implements the Kubernetes DNS-based service discovery specification and handles all the service.namespace.svc.cluster.local queries in your cluster. Let's walk through how it works and how to configure it. At its simplest, you add Kubernetes to your server block for the cluster.local. CoreDNS connects to the Kubernetes API in cluster using the service account, watches services and endpoints, and answers queries based on what it finds. When a pod queries myservice.default.svc.cluster.local, the Kubernetes plugin looks up the service named myservice in the default namespace, finds its cluster IP, and returns that as an A record. For headless services, it returns the individual pod IPs instead. The basic syntax is just Kubernetes followed by optional zones. If you don't specify zones, it defaults to the server block zone. In production Kubernetes, you'll usually see Kubernetes cluster.local. Now let's talk about the configuration options. The endpoint option specifies a remote Kubernetes API URL. If you don't set this, CoreDNS connects in cluster. If you're running CoreDNS outside the cluster, you'd specify your API server URL here. For authentication to remote clusters, you have two options. The TLS option takes certificate, key, and CA-cert files. Or use kubeconfig to authenticate via a kubeconfig file, optionally specifying a context. The namespaces option filters which namespaces CoreDNS exposes. By default, it exposes all namespaces. If you only want certain namespaces visible via DNS, list them here. The labels option filters by Kubernetes labels. Only services and endpoints matching your label selector appear in DNS. This is powerful for multi-tenant clusters where you want DNS isolation. The pods option controls how CoreDNS handles pod A records. By default, it's disabled. Pod queries return NX domain. The insecure mode returns an A record for any IP without verification, which is vulnerable to abuse. The verified mode checks that a pod with that IP actually exists, but uses more memory because it watches all pods. The endpoint_pod names changes how endpoint names are formed. Instead of using the dashed IP format like 10.0.1.5, it uses the actual pod name. This is useful when you need meaningful names in your DNS records. TTL defaults to 5 seconds. You can set it anywhere from 0 to 3600 seconds. 0 means no caching, fresh data every time. Higher values reduce API load but introduce staleness. The No Endpoints option disables endpoint watching entirely. All endpoint and headless service queries return NX domain. Use this if you only need cluster IP resolution and want to reduce API server load. The fall-through option passes queries to the next plugin when the Kubernetes plugin returns NX domain. Useful when you have another plugin handling queries the Kubernetes plugin can't. The Ignore Empty Service option returns NX domain for services with no ready endpoints. This lets the client continue searching through its search path, potentially finding the service in another cluster.
For multi-cluster setups using the Multi-Cluster Services API, the Multi-Cluster option defines additional zones for service import resources. You'd typically pair this with an MCS implementation. The Startup Timeout option controls how long CoreDNS waits for API synchronization on startup. Default is 5 seconds. If sync hasn't completed, CoreDNS starts anyway, but returns serve fail for Kubernetes queries until sync completes. Now let's talk about what happens under the hood. The Kubernetes plugin watches endpoints via the Endpoint Slices API. When pods start or stop, when services change, those updates flow through and CoreDNS's cache updates. There's typically a few seconds of latency between a Kubernetes change and DNS reflecting it. The plugin reports readiness to the Ready plugin. It won't mark itself ready until it has synchronized with the Kubernetes API. This prevents traffic hitting CoreDNS before it can answer correctly. For PTR records, reverse DNS lookups, the Kubernetes plugin creates a PTR for every pod selected by a service. If a pod is selected by multiple services, it gets multiple PTR records. The metrics exposed when you're using the Prometheus plugin include DNS programming latency, API request latency, rate limiter duration, and request counts. These are essential for understanding CoreDNS performance in your cluster. A common production configuration handles the cluster.local zone, plus reverse DNS for your pod CIDAR, pods verified mode for accurate pod DNS, forward to upstream for everything else, add caching, logging, health, ready, and metrics. That's a production-ready CoreDNS for Kubernetes.
The forward plugin is how CoreDNS talks to upstream DNS servers. It proxies queries to resolvers you specify and handles the complexity of load balancing, health checking, and failover. Let's break down how it works. The basic syntax is simple: forward, followed by the domain to match, followed by your upstream servers. Forward.8.8.8 9.9.9 forwards all queries to Google and Quad 9 DNS. You can specify up to 15 upstreams. The forward plugin is smart about connections. It reuses already open sockets to your upstreams. It supports plain DNS, DNS over TLS, and TCP. Health checking happens automatically, in band with your traffic. Here's how health checking works. When the plugin detects an error, a timeout, a network failure, it starts health checking that upstream. Every half second, it sends a recursive query asking for the root name servers. Any response that isn't a network error counts as healthy. Once healthy, the checks stop until the next error. If all upstreams go down, CoreDNS assumes health checking has failed as a mechanism. It starts sending queries to random upstreams anyway, because sometimes that works when health checks don't. Let's walk through the configuration options. The Accept option excludes certain domains from forwarding. If you forward everything to 8.8.8.8 except your internal domains, those internal queries fall through to the next plugin. Force_TCP forces TCP even when the request came in over UDP. Prefer_UDP tries UDP first even for TCP requests, retrying on TCP if the response is truncated. If you specify both, force TCP wins. Max_fails controls how many consecutive health check failures mark an upstream as down. Default is 2. Set it to 0 to disable health checking entirely. The upstream is always considered healthy. Expire sets how long to keep cached connections. Default is 10 seconds. Longer values reduce connection setup overhead but use more resources. For TLS upstreams, you have several options. Just TLS uses system CAs with no client auth. TLS CA specifies a custom CA file. TLS cert key enables client auth with system CAs. TLS cert key K does client auth with a custom CA. The TLS underscore server name is critical. For DNS over TLS, you need to specify the server name for TLS negotiation. Without it, anyone can man-in-the-middle your connection. For Quad 9, use dns.quad9.net. For Cloudflare, use cloudflare-dns.com. This is strongly recommended. One limitation, the TLS config is global for the entire forward statement. If you need different TLS server names for different upstreams, you need multiple server blocks forwarding to local ports, each with their own TLS configuration. The policy option controls upstream selection. Random is the default. Upstreams are randomized on first use. Round robin cycles through them in order. Sequential always tries the first one first, then the second, and so on. Health check lets you tune the checking interval. Default is half a second. You can also disable the recursion desired flag with no rec and change the domain used for checks. Max concurrent limits simultaneous queries to prevent overwhelming your upstreams. Queries that would exceed this limit get refused responses. Pick a number based on your expected query rate times upstream latency. Each concurrent query uses about 2 kilobytes of memory. The next option is interesting. If an upstream returns a specific response code, like NX domain, forward passes the query to the next plugin. This lets you chain multiple forwards with fallback behavior. Fail fast all unhealthy upstreams immediately returns serve fail when all upstreams are down, instead of trying random ones. Failover makes forward retry on other upstreams for specific response codes, not just network failures. If you want to retry on NX domain or refused, use this. The metrics exposed include request duration histograms, health check failures, and connection cache statistics. These are essential for understanding forwards behavior in production. A common production setup forwards to DNS over TLS upstreams with proper server names, includes health checks every 5 seconds to avoid overwhelming the service, and caches responses for 30 seconds. That's secure, resilient, and performant.
The cache plugin is straightforward but critical. It caches DNS responses so you don't hammer your backends on every query. By default, all records except zone transfers and metadata are cached for up to 3,600 seconds. No error responses can be cached for an hour. Denial of existence responses for 30 minutes. Each response is cached according to its own TTL, but won't exceed your configured maximum. The basic syntax is just cache, optionally followed by a max TTL and zones. Cache 300 caps caching at 5 minutes. Cache 300 example.org only caches for that zone. Under the hood, the cache is sharded into 256 pieces, each holding about 39 items by default. That's roughly 10,000 items total. When a shard fills up, eviction is random, not based on TTL or access time. This is important to understand. Items with 0 TTL stay in cache until randomly evicted. For more control, you have several configuration blocks. The Success option configures caching for successful responses. You specify a capacity, an optional max TTL, and an optional minimum TTL. The minimum TTL is useful to prevent very short TTLs from causing a flood of queries to your backend. Default minimum is 5 seconds. The denial option works the same way, but for NXDON and other negative responses. These use LRU eviction instead of random. Prefetch is a performance optimization. When a cached item is about to expire and it's been queried frequently, CoreDNS proactively refreshes it before it expires.
You configure the threshold of queries that count as popular and what percentage of TTL remaining triggers prefetch. Default is 10%, meaning when a popular item has 10% of its TTL left, CoreDNS refreshes it. Serve stale is for resilience. If your backend is down and you have an expired entry, serve stale will return that stale response with a TTL of 0. Better to return old data than fail completely. You can configure how long to keep serving stale entries. Default is 1 hour. There are 2 refresh modes. Immediate sends the stale response while refreshing in the background. Verify checks if fresh data is available first. Serve fail caching prevents repeated queries from hammering a misbehaving backend. By default, serve fail responses are cached for 5 seconds. You can increase this up to 5 minutes or disable it with 0. The disable option turns off caching for specific zones. Useful when you have zones that need fresh data every time. Keep TTL is for when CoreDNS is authoritative. Instead of decrementing TTLs as time passes, it serves the original TTL until the entry expires. Don't use this for caching external data. You'll serve stale answers that claim to be fresh. The cache metrics are essential for understanding what's happening. Cache entries shows how full each cache type is. Hits and misses tell you your cache efficiency. Prefetch counts show if that feature is helping. Served stale tells you when your resilience mode kicked in. Evictions show if your cache is sized appropriately. A practical production configuration might use success 10,000 for a larger cache, denial 5,000 for negative responses, prefetch 10, 1M, 10% to keep popular items fresh, and serve stale 1 hour to handle back-end outages. That gives you performance, resilience, and observability.
The File plugin serves DNS zones from traditional zone files. This is classic DNS server behavior, the same format used by Bind for decades. You create a zone file in RFC 1035 format, point the File plugin at it, and CoreDNS serves it. If your zone file includes DNSSEC signatures, CoreDNS serves those too. Only NSC is supported for DNSSEC, not NSC3. And you're responsible for re-signing the zone file when records change. The basic syntax is file, followed by your zone file path, and optional zones. If you don't specify zones, it uses the zone from your server block. A relative path gets the root plugin's directory prepended. Let me walk through a typical zone file. You start with an @origin directive, setting the default domain. Then your SOA record with the primary name server, contact email, serial number, and timing values. Then NS records, pointing to your name servers. Then your actual A, AA4, CNAME, MX, and other records. Here's the critical part, the serial number in your SOA record. Every time you change the zone file, increment the serial. CoreDNS watches for serial changes and reloads automatically. The reload option controls how often CoreDNS checks for changes. Default is 1 minute. You can set it to 30 seconds for faster updates or 0 to disable automatic reloading entirely. When the serial number changes, CoreDNS reloads the zone without a restart. The fall-through option passes queries to the next plugin if no record matches. Useful when you want to serve some records from a zone file and let another plugin handle the rest. One common mistake, specifying a zone file for the root zone without setting the origin correctly. If your server block is for the root zone, but your file is db.example.org, CoreDNS reads that file with root as the origin. Your records won't resolve as expected. Be explicit. Either use file db.example.org, example.org, or put the file plugin in an example.org server block. For zone transfers, combine the file plugin with the transfer plugin. The file plugin serves the zone data, the transfer plugin handles AXFR and IXR requests.
You can allow transfers to everyone or restrict to specific IP addresses. You can serve multiple zones from a single zone file by listing them after the file path. This is useful for similar zones that share most records. The file plugin is straightforward when you understand zone file format. The RFC 1035 specification defines the format, and there are countless examples online. If you've ever edited bind zone files, you already know how to use this.
The Hosts plugin serves DNS from a hosts file, the same format as etc hosts. Simple, familiar, and useful for quick overrides. If you've ever edited etc hosts to block ads or redirect a host name, you know the format. Each line has an IP address followed by one or more host names. The first host name is canonical, the rest are aliases. By default, the Hosts plugin reads etc hosts. You can specify a different file or even inline the entries directly in your Corefile. It only supports A, AAA, and PTR records. No CNAME, no MX, just address mappings. The plugin watches the file and reloads every 5 seconds. Change your hosts file, CoreDNS picks it up automatically. If you delete the file, any inline content keeps serving. When the file comes back, it's used again. One nice feature, PTR records for reverse lookups are generated automatically. You add a forward mapping, you get the reverse mapping for free. If you don't want this, use the No Reverse option. The syntax is hosts, optionally followed by a file path, and zones. No arguments means use etc hosts. Specify a path to use a custom file. List zones to restrict what domains the plugin handles. You can define hosts in line in your Corefile. Put entries between hosts and fallthrough, each on its own line. This is handy for a few overrides without maintaining a separate file. File entries and inline entries combine, with inline taking precedence. The TTL option sets the TTL for generated records. Default is 1 hour. The reload option changes how often CoreDNS checks the file. Default 5 seconds. Set it to 0 to disable automatic reloading. The fallthrough option is important. By default, if a query matches the zone but no record exists, the Hosts plugin returns NX domain. With fallthrough, it passes the query to the next plugin instead. You almost always want this when combining hosts with other plugins. A common use case, blocking ad servers. There are public hosts files with thousands of ad domains mapped to 0.0.0. Point the Hosts plugin at one of these, and those domains go nowhere. Combined with fallthrough, so legitimate queries go to your Upstream resolvers. Another use case, local development overrides. Map your production domains to localhost or staging IPs while developing. Quick and easy, no need to mess with your system's etc hosts. The Hosts plugin exposes 2 metrics, the number of entries loaded and the timestamp of the last reload. Basic, but enough to confirm it's working. Remember, Hosts only does address records. For more complex zones with MX, CNAME, SRV, or other record types, use the File plugin instead. Let's talk about errors and logging in CoreDNS. The Errors and Log plugins work together to give you visibility into what's happening. The Errors plugin enables error logging. When something goes wrong, a backend timeout, a parsing error, any kind of failure, Errors writes it to standard error with a timestamp. The basic syntax is just errors in your server block. By default, it logs errors using the standard format. You can customize the format and consolidate repeated errors to avoid log flooding. Consolidation is useful when you have the same error repeatedly. Instead of logging every occurrence, errors can consolidate them and report 5 errors like this in the last 30 seconds. Use errors consolidate v1.13.1 to enable it. The log plugin records every DNS query that passes through CoreDNS. This is your audit trail and your debugging lifeline. By default, log writes to standard output in the combined log format from Caddy. You see the timestamp, client address, query ID, query type, query class, query name, protocol, request size, DNSSEC DO bit, buffer size, response code, response flags, response size, and duration. A typical log line tells you everything about what happened. Info 192.168.1.5:43821 12345 AAA in myservice.default.svc.cluster.local UDP 85 false 4096 NOR QR AA RD 156.0.00654S. That shows a successful query from a client asking for an IPv6 address of a Kubernetes service answered in under a millisecond. You can customize the log format. The Format option takes a template string with placeholders. Common placeholders include remote for client address, type for query type, name for query name, rcode for response code, and duration for how long it took. The Class option filters which queries to log. You can log only denial responses, only error responses, or only specific zones. This helps reduce log volume while keeping important information. In production Kubernetes, you typically want errors enabled always. For logging, you might enable it during debugging but disable it in production due to volume. Prometheus metrics give you aggregated statistics without the log overhead. One common pattern, enable log with class denial to capture all NXDON responses. These indicate failed lookups, which might mean misconfigured services or DNS resolution problems. You get alertable events without logging every successful query. Remember that log and errors write to standard output. In Kubernetes, that means your logs go to the container runtime and can be collected by your cluster's logging solution, FluentD, Loki, whatever you're using. Structure your log format to make it easy to parse and search. Let's cover the Health and Ready plugins together. They're essential for running Kubernetes in Kubernetes. The Health plugin provides a liveness probe endpoint. By default, it listens on port 8080 at the /health path. When CoreDNS is running and responsive, it returns HTTP 200 OK with OK in the body. The key thing to understand, Health only needs to be enabled once. Even if you have multiple server blocks, one health declaration enables it globally for the entire CoreDNS process. The syntax is simple. Just health in any server block. You can optionally specify a different address with health:8081 or health 127.0.0.1:8080. The default is :8080. There's one option, lame duck. When CoreDNS receives a shutdown signal, lame duck delays the shutdown for a specified duration while still serving requests but reporting unhealthy to health checks. This lets load balancers drain traffic gracefully. Health lame duck 5S gives you a 5-second drain window. The Ready plugin is different. It provides a readiness probe endpoint, separate from liveness. By default, it's at port 8181 on the /ready path. Ready reports whether CoreDNS is ready to receive traffic. This is critically important in Kubernetes. A plugin that reports not ready makes the entire CoreDNS instance unready. For example, the Kubernetes plugin reports not ready until it has synchronized with the Kubernetes API. If CoreDNS started serving before sync completed, it would return serve fail for all Kubernetes queries. The Ready plugin prevents that. The syntax is just ready or ready:8282 for a different port. In Kubernetes deployments, you configure liveness probe to hit the health endpoint and readiness probe to hit the ready endpoint. The liveness probe catches if CoreDNS has hung or crashed. The readiness probe catches if CoreDNS can't yet serve your traffic correctly. A typical Kubernetes probe configuration uses HTTP GET to port 8080 path health for liveness, with initial delay of 60 seconds and period of 10 seconds. For readiness, HTTP GET to port 8181 path ready with period of 2 seconds. The reason for separate endpoints. CoreDNS might be alive but not ready. You don't want Kubernetes killing a pod that's just slow to start. You want to stop sending it traffic until it's ready, which is what Readiness Probe does. These two plugins together give you proper Kubernetes integration for high availability. Health catches crashes and hangs, Ready catches incomplete initialization. Lame duck handles graceful shutdown. That covers the lifecycle. The Prometheus plugin, also called Metrics, exposes CoreDNS statistics for Prometheus to scrape. If you're serious about running CoreDNS in production, this is non-negotiable. By default, metrics are exposed on port 9153 at the metrics path. Just add Prometheus to your Corefile and you have observability. The syntax is simple. Prometheus uses defaults. Prometheus 9253 changes the port. Prometheus localhost 9153 binds to localhost only. Like the Health plugin, Prometheus only needs to be enabled once. Even with multiple server blocks, one declaration enables it for everything. Now let's talk about what metrics you get. At the core level, you get CoreDNS DNS requests total, a counter of total queries by server, zone, protocol, family, and type. This tells you your query volume and what kinds of queries you're handling. CoreDNS DNS responses total counts responses by server, zone, R-code, and plugin. This shows you success rates and what response codes you're returning. CoreDNS DNS request duration seconds is a histogram of query latency. This is your SLO metric. How fast is CoreDNS responding? CoreDNS DNS request size bytes and CoreDNS DNS response size bytes show you request and response sizes, useful for capacity planning. Many plugins add their own metrics. The Cache plugin adds cache hits, cache misses, cache entries, and prefetch counts. The Forward plugin adds upstream latency, health check failures, and connection cache statistics. The Kubernetes plugin adds API latency and programming duration. When you're monitoring CoreDNS, focus on a few key things. First, latency. The P99 of CoreDNS DNS request duration seconds should be well under your application timeout. In most cases, you want DNS responses in single-digit milliseconds. Second, error rate. Calculate the ratio of serve fail and refused responses to total responses. In a healthy cluster, this should be essentially 0. Third, cache hit rate. Divide cache hits by total cache requests. Higher is better. If your hit rate is low, you might need to tune TTLs or increase cache size. Fourth, forward health. Watch CoreDNS forward health check broken total. If this is incrementing, all your upstreams are unhealthy, and CoreDNS is randomly spraying queries hoping one works. Fifth, Kubernetes API latency. The CoreDNS Kubernetes REST client request duration seconds metric shows how fast CoreDNS can talk to your API server. High latency here means slow DNS for service discovery. A standard Prometheus rule might alert when DNS latency P99 exceeds 50 milliseconds, when error rate exceeds 1%, or when all forward upstreams are unhealthy. Fifth, Kubernetes API latency. The CoreDNS Kubernetes REST client request duration seconds metric shows how fast CoreDNS can talk to your API server. High latency here means slow DNS for service discovery.
A standard Prometheus rule might alert when DNS latency P99 exceeds 50 milliseconds, when error rate exceeds 1%, or when all forward upstreams are unhealthy. The Prometheus plugin also reports whether DNS over TLT and DNS over HTTP are in use, how many panics CoreDNS has recovered from, and build information like version and go version. With Prometheus enabled and proper dashboards, you have full visibility into CoreDNS behavior. That's essential for production operations.
The Rewrite plugin is one of the most powerful in CoreDNS. It lets you transform DNS queries and responses on the fly, invisible to the client. You can rewrite query names, query types, response TTLs, response codes, and even CNAME targets. Let me walk through the key use cases. Name rewriting is the most common. Say you're migrating from one domain to another, or you want to translate internal names to external ones. The Rewrite plugin can match exactly, by prefix, suffix, substring, or regular expression. A simple suffix rewrite might translate .example.internal to .example.com. A regex rewrite can capture groups and insert them into the new name. You can transform service.us-1.example.org into service.us-1.console. Here's the critical concept. When you rewrite the query name, you also need to rewrite the response. Some DNS resolvers detect mismatches between the question and answer sections as potential attacks. The answer option handles this. For simple cases, use answer auto. CoreDNS figures out how to reverse your transformation. For complex regex rewrites, you specify an explicit answer rule that transforms the response names back. Type rewriting changes the query type. If you want to rewrite any queries to hinfo, rewrite type any hinfo does it. This is useful for security since any queries can be used in amplification attacks. Class rewriting changes the DNS class. Most queries are class IN for Internet, but sometimes you need to handle CH for chaos or HS for Hesiod. TTL rewriting modifies response TTLs. If an upstream returns 0 TTL preventing caching, you can bump it up. If responses have excessive TTLs causing stale data, you can cap them. You can set a specific value or a range. CoreDNS clamps to that range. Response code rewriting changes the R code. If an upstream returns serve fail but you want to return no error, you can transform it. Useful for working around misbehaving backends. CNAME target rewriting is specialized but powerful. If your application follows a CNAME and you need to redirect it to a different target, rewrite CNAME transforms the CNAME target and regenerates the answer records. The continue and stop keywords control rule chaining. By default, once a rule matches, processing stops. With continue, CoreDNS keeps applying rules. For response rewrites with multiple matching rules, the response rewrite happens in reverse order. Last matching rules response rewrite applies first. eDNS 0 rewriting lets you manipulate extension options. You can set, append, replace, or unset specific eDNS options. This is advanced but useful for things like client subnet tagging. Here's a practical example. You're running a service mesh where external clients use different names than internal services. Rewrite incoming queries from the external namespace to the internal one. Let CoreDNS resolve against your service mesh, then rewrite the responses back. The client sees external names, the backend sees internal names, and nobody knows the difference. The Rewrite plugin is complex but worth understanding. It solves problems that otherwise require custom code or awkward workarounds. The ACL plugin provides access control for CoreDNS. You can block, filter, or drop DNS queries based on source IP and query type. This is your first line of defense against unauthorized access, amplification attacks, and noisy clients. The syntax defines rules with an action, optional query types, and source networks. Actions are allow, block, filter, or drop. Allow is the default for queries that don't match any rule. The difference between block, filter, and drop is important. Block returns refused. The client knows their query was denied. Filter returns no error with an empty answer. The client thinks there's just no record. Drop returns nothing at all. The client times out. Choose based on whether you want the client to know they're being blocked. Query types let you target specific record types. Block type A to prevent address lookups. Block type any to prevent amplification attacks. Use asterisk to match all types. Source networks use CIDR notation. Block 192.168.0/16 to block an entire internal range. Allow 10.0.0.8 to permit your internal network. Asterisk matches all IPs. Rules are evaluated in order. The first matching rule wins. This lets you create exception patterns. Allow a specific subnet, then block the broader network. Here's a common pattern for public DNS. Allow your trusted networks, block everyone else. Put the allow rules first, then block with no arguments as a catch-all. Another common pattern, rate limiting abusers. If you see a specific IP hammering you with queries, add a block rule for that IP. The metrics will confirm it's working. For Kubernetes internal DNS, you typically want to allow all queries from the pod network and block everything else. This prevents external clients from querying your cluster DNS. One caveat: the ACL plugin sees the source IP from the TCP or UDP header. If queries pass through a forwarding DNS server, the source IP is the forwarder, not the original client. Same for source net. This affects your rule design. The plugin exports metrics for allowed, blocked, filtered, and dropped requests. Use these to verify your rules are working and to understand your traffic patterns. You can use the ACL plugin multiple times per server block. This lets you organize rules logically or build complex policies incrementally. The ACL plugin is simple but essential. Every production CoreDNS deployment should consider access control.
Let's cover two security-focused plugins, DNSSEC for signing responses and DNTAP for deep packet logging. The DNSSEC plugin enables on-the-fly DNSSEC signing. Any response that isn't already signed gets signed before it leaves CoreDNS. This is useful when you're serving zones that aren't traditionally signed, but you want DNSSEC validation. DNSSEC works by cryptographically signing DNS records. Resolvers can verify these signatures to ensure responses haven't been tampered with. Without DNSSEC, DNS queries are vulnerable to spoofing attacks. CoreDNS implements authenticated denial of existence using NSC blacklies. This is a simplification that avoids the complexity of full NSC zone walking. NSC 3 is not supported. For algorithm, ECDSA is preferred because it produces smaller signatures than RSA. To configure DNSSEC, you need keys. Generate them using DNSSEC keygen from bind. DNSSEC-keygen-A ECDSA P256 SHA256 your zone name. This creates public and private key files. Point the DNSSEC plugin at your key files using key file followed by the key base name or full file name. You can specify multiple keys. If you have keys with and without the SEP bit set, CoreDNS does split KSK-ZSK signing. Otherwise, it treats each key as a combined signing key. For production, you might store keys in AWS Secrets Manager instead of on disk. The Key AWS Secrets Manager option fetches keys from AWS using the standard SDK credentials. The Cache Capacity option controls how many signatures to cache. Default is 10,000.
Caching prevents re-signing the same records repeatedly. One important limitation, the DNSSEC plugin doesn't know original TTLs, so it always uses 3600 seconds for signatures. Now let's talk about dntap. This is a structured binary logging format for DNS traffic. Think of it as deep packet inspection for DNS, useful for security analysis, debugging, and compliance. The dntap plugin sends every query and response to a Unix socket or remote endpoint. You can capture the full wire format DNS message or just metadata. Messages are buffered, default 10,000 messages, and dropped if the buffer fills. The basic syntax is dntap followed by a socket path or remote address. Add full to include the complete DNS message. You can override identity and version fields and add extra metadata. For local debugging, point dntap at a Unix socket and use the dntap command line tool to decode messages. For production logging, send to a remote collector over TCP or TLS. You can use multiple dntap plugins to send to different destinations, one for local debugging, one for a remote SIEM, whatever your architecture needs. The dntap protocol is documented at dntap.info. The command line tool is available from GitHub. It's a standard in DNS infrastructure for deep visibility. Together, DNSSEC and dntap give you security signing and visibility logging, two different aspects of DNS security, both important for production deployments.
Let's cover some additional plugins that round out a production CoreDNS deployment: Auto, Load Balance, and Loop. The Auto plugin is like the File plugin, but it automatically discovers zone files from a directory. Instead of explicitly listing each zone in your Corefile, you point Auto at a directory and it picks up every zone file it finds. Files are matched using a regular expression. The default pattern is db.star, so a file named db.example.com gets loaded as the example.com zone. You can customize this pattern to match your naming convention. When zone files change, Auto detects the new SOA serial and reloads. You configure how often it scans with the reload option. Default is 1 minute. This lets you add new zones or update existing ones without restarting CoreDNS. This is useful when you manage many zones. Instead of editing your core file for every zone change, you just add or modify zone files. CoreDNS picks them up automatically. The Load Balance plugin randomizes the order of A, AAA, and MX records. This is classic round-robin DNS load balancing. Each client gets records in a different order, spreading load across multiple servers. The basic mode is random shuffling. Add load balance round_robin, and every response gets shuffled. Simple and effective. For more control, weighted mode lets you bias the distribution. Assign weights to IPs in a weight file, and the load balancer prefers higher weighted addresses. A weight of 3 means that IP appears first 3 times as often as a weight 1 IP. The Prefer option reorders records to put specific subnets first. If you want local IPs before remote ones, list your local subnets with Prefer. Responses get reordered so matching IPs come first. One detail, load balance sorts CNAMEs before address records. Some stub resolvers, like glib, are picky about record ordering, and this keeps them happy. The Loop plugin detects forwarding loops and halts CoreDNS before it consumes all your memory. A forwarding loop happens when CoreDNS forwards to itself, either directly or through another server that forwards back. How does it work? On startup, Loop sends a random probe query to itself. If it sees that query come back more than twice, it's a loop. CoreDNS logs the loop and exits. This is a safety net. Loops are usually configuration mistakes, forwarding to 127.0.1 or forwarding to etcresolve.com when that file points to localhost.
Without loop detection, CoreDNS would spin forever, eating CPU and memory until the system dies. In Kubernetes, loop detection is critical. The default CoreDNS configuration forwards to etcresolve.com. On nodes running systemd resolved, that file often contains 127.0.53. CoreDNS forwards to itself, detects the loop, exits, Kubernetes restarts it, and you get crash loop backoff. The fix is to configure kubelet with the real resolve.com path, or hardcode upstream IPs in your Corefile instead of using etcresolve.com. The loop plugin documentation has detailed Kubernetes troubleshooting steps. These plugins might seem minor, but they're important for production. Auto simplifies zone management, load balance spreads load, loop prevents catastrophic failure. Include them in your production Corefile.
Let's wrap up what we've covered about CoreDNS. 3 key takeaways. First, CoreDNS is radically simple. Everything is a plugin. The Corefile is just zones mapping to plugins. Once you understand that mental model, configuration becomes straightforward. You pick the plugins you need, configure them in your server blocks, and CoreDNS handles the rest. Second, for Kubernetes, CoreDNS is critical infrastructure. Every service-to-service call starts with DNS. If CoreDNS is slow or unreliable, your entire cluster feels it. Run at least 2 replicas. Monitor latency and error rates. Use the Health and Ready plugins for proper lifecycle management. Third, observability is essential. The Prometheus plugin gives you cache hit rates, query latency, upstream health, and API client performance. The Log and Errors plugins give you detailed debugging information. Use them, set up alerts. CoreDNS is too important to run blind. When should you use CoreDNS? For Kubernetes service discovery, it's the default and the right choice. For internal DNS in your organization, it's flexible and powerful. For a recursive resolver or forwarding proxy, it works well with the right plugins. When might you look elsewhere? For authoritative DNS at massive scale, serving millions of external queries, dedicated infrastructure like Route 53 or Cloud DNS is typically a better fit. CoreDNS can do it, but it's not the sweet spot. For more information, check the official documentation at coredns.io. The plugin documentation is comprehensive. The CNCF Slack has an active CoreDNS channel for community support. And the GitHub repository has issues and discussions where you can find solutions to common problems. All the links are in the show notes. Thanks for listening.
That's it for this episode of AudioDocs by Platform Engineering Playbook. If you spotted any issues with these audio docs, leave a comment or open a pull request. Every script and transcript lives out in the open at platform-engineering-playbook.com. Finally, if you found this valuable, consider subscribing and giving this video a thumbs up to help others discover our content. Thanks for listening, and see you next time inside the Platform Engineering Playbook.